first let's look at what we did in lecture number 16. So in lecture number 16 we were studying parametric down conversion as a non-linear optical process that can produce two-photon entangled state, and we looked at in quite some detail. Earlier we had derived the two-photon state produced by parametric down conversion using the quantum formalism, and then we found that the two-photon state produced by down conversion is represented by an integral like this, and this thing is what's known as phase matching function. And in the last lecture we looked at this phase matching function in quite some detail, although this is a very simple looking integral, but we saw that this kpz, ksz, kiz, these depend on several parameters, including the birefringence of the crystal, polarization, its direction, wavelength, and so on. So we looked at all these things in details. We also looked at the possible ways or the possible scenarios in which the polarization comes into phase matching, satisfying the phase matching condition. As more specifically, we saw that there are two ways in which phase matching can be satisfied as far as polarization is concerned. One is called the type 1 phase matching. In this, both the entangled photons, the down converted photons, have the same polarization. Type 2 phase matching condition, both the entangled photons can have the opposite polarization. One is extraordinary, other one is ordinary, and vice versa. And then we also looked at the effect of different pump and crystal parameters on phase matching. These we looked at in detail. I also presented some of the numerical simulation work that we do using a program that we have written. And I also presented some of the experimental results just to kind of emphasize that the theory very accurately matches what one can actually see in the labs. So this was the two-photon state produced by parametric down conversion, and we saw how this state can be tweaked by changing the phase matching conditions and constraints, by changing different crystal parameters or pump parameters, and so on. Now today we are going to study the two-photon interference these entangled two photons produce. I'll try to present the temporal two-photon interference with an intuition that is pretty much same as what we did in the classical interference as well as in one-photon temporal interference. So this is a very generic interferometer. This is a representative two-photon interferometer. So I will try to explain the basics of temporal two-photon interference using this interferometer, but whatever we do with this interferometer will be very, very general. So I will try to, today's lecture will try to kind of work things out in with all the mathematical details, and in the next lecture I'll try to give some intuitive, more intuitive understanding of how these interference actually work. So today's lecture will try to work things out in mathematical detail and rigor, and also I'll have these maths being posted as lecture notes. Okay, so let's get started with this temporal two-photon interference. So this is a representative two-photon interferometer. In this, we have this pump photon hitting this parametric down conversion crystal, and then it goes here and then comes back. So now there are two ways in which the entangled photons can get produced. One is when this pump is going through this crystal in the forward direction, these two photons can get produced. Or it may happen. It can also happen that the pump photon doesn't get down converted in its forward pass, but when it comes back, it actually gets down converted. So there are two possible ways in which the down conversion of the pump photon can happen, and then subsequently the down converted photons can reach these detectors. So in one possibility, this is the first possibility, in which the pump photon does not get down converted in its forward pass. It goes here, comes back, and then in its backward pass it actually gets down converted. The second alternative is the pump photon does get down converted in its forward pass, and then these two entangled photons go in these directions, they get reflected back from these mirrors, and then they reach the respective detectors. So if we actually observe a coincidence count, that means one photon here and one photon there at these two detectors, then there are two possible ways in which that can happen, which is this and this. And typically there is no way that one can tell just by looking at the coincidence whether this event happened or that event happened. This is same as when we do a Young's double slit experiment with single photons, and there is no way of telling whether the photon goes through first slit or the second slit, and then we say that the interference is because of the interference of those two alternatives. Similarly, here when we detect a coincidence, that means one photon here, one photon there, there is no way of telling whether the down conversion and the subsequent entangled photons reaching the detector, if that happened in this manner or in this manner. So these are the two possible alternative ways in which the down conversion can happen and the down converted photons can get to the detector. And in any interference, we always need two possible alternatives, and so these are the two photon alternatives. Now, in order to explain this, we'll actually present this in terms of an unfolded diagram. So, for example, this alternative we can represent like this, where LP1, this represents the path length traveled by the pump photon in alternative 1. So, this is the pump, so that's the total path length traveled is this one. So, that's the LP1 and we are representing it like this. LS1 is the path length traveled by the signal photon in alternative 1, which in this case would be just this. Similarly, LS2 is the path length traveled by the signal photon in alternative 2, which in this case would be signal is this. So, that is the length which is LS2 and so on. Phi P1, these are the extra phases. These come because of geometric phase or phases introduced by reflection from mirrors, beam splitters and so on. So, these are the additional phase that these photons can accumulate and that we are actually showing here. So, in general, we have these two alternatives, and in these two separate alternatives, the pump, the signal and the idler photons can have different path lengths that they have traveled. Okay, now before proceeding further, let's just define some length parameter. We'll see that these become very useful in studying these interference and also comparing two photon interference with the one photon interference in a very analogous manner. So here we have these 6 different length parameters that usually get involved in any two photon interference. And also I should note that at the level of these diagrams, there is really no, these diagrams are not really associated with this interferometer only. For any two photon interference, we can always represent that in terms of this unfolded two photon path diagrams. So once we have this two photon path diagram, then the subsequent analysis we do is not necessarily just limited to this particular interferometer, but it can be any two photon interferometer for that matter. Okay, so and again the interference will happen whenever this alternative is indistinguishable from this alternative, or when this alternative is coherent with respect to this alternative. If these two alternatives are not coherent, then interference cannot happen. This is very similar to when we say in Young's double slit, if the field coming from first slit is coherent with the second slit, field coming from the second slit, only then the interference can happen. So here let's define now some length parameters which will be very useful in our subsequent analysis, and also establishing connections analogy with one photon interference. So first of all, we define L1. This L1 we define as LS1 plus Li1 by 2 plus LP1. So this is the length traveled by the pump photon and the average length traveled by the signal idler photon. So that's the LS1. So that's LP1 plus LS1 plus Li1 divided by 2. So that's the L1. Similarly, let's define L2, which is the length traveled by pump plus the average length traveled by signal idler photon in alternative 2. And their difference we'll call delta L. This is also called the two photon path length difference. Let's also define an L1 prime. L1 prime is the difference of the path length traveled by the signal and idler photon in alternative 1. So that's the L1 prime. Similarly, L2 prime is the difference of the path length traveled by the signal idler photon in alternative 2. So that we represent as L2 prime. And their difference, L1 prime minus L2 prime, that we represent by delta L prime. So this is two photon path asymmetry length, as we call it. We can also define this phi 1 and phi 2, which phi 1 is basically phi S1, phi I1, phi P1, which is all the phases in alternative 1. Phi 2 has all the phases in alternative 2, and the difference we'll call delta phi. So this delta L prime, delta L phi, these are the 3 quantities we have, and we'll see that these will be very useful in describing and understanding two photon interference in a very similar and analogous manner as we do one photon interference. Okay, so that's a representative interference, a two photon interference at the level of path diagram. This can represent any two photon interference, and here is some generic path length parameters and phase parameters that we have defined, which will be useful in our analysis. Okay, so now we want to actually derive that for a general two-photon interference, what is the coincidence count rate that one detects at these two detectors DS and DI. So here is the down conversion, and then we want to get the coincidence as a function of the two-photon interference. So first of all, what is the two-photon state produced by parametric down conversion? So this is the two-photon state. This we have already derived. Here we are writing in terms of omega p and omega t. So this is the two-photon state produced by parametric down conversion. Now when we are talking about interference, we always have at least two alternatives. And here we are only talking about the interference situation when we have two alternatives. So if there are two alternative ways in which the down conversion can happen, here we saw that this is the forward pass and backward pass are the two alternative ways. So when there are two alternative ways, then the total two-photon state produced by PDC is the sum of the two-photon state produced in two separate alternatives. So for example, psi TP1 is the two-photon state produced in the forward pass, psi TP2 is the two-photon state produced in the backward pass. So the total two-photon state we can write like this. So this is just the same, this is exactly the same state, except that we are adding these two, and then we are representing everything here by the index 1 to say that this is alternative 1, and this one by index 2 to say that this is from alternative 2. And the total two-photon state is the sum of the states produced in these two alternatives. So that's a two-photon state that is produced by parametric down conversion. Again, the two-photon state here is this psi TP1 is the two-photon state produced in alternative 1 right at the exit phase of the crystal, and psi TP2 is the two-photon state produced in alternative 2 at the exit phase of the crystal, and psi is the sum of the two states. Now before we can calculate any meaningful quantity with this state, we need to calculate the field operators at the signal IIT detector. So the field operator at the signal detector ES, that's the positive frequency part. So the field operator at time t at the detector is given by, or is the sum of the field coming to the detector in alternative 1 and in alternative 2. So whatever was the field here, it reaches the detector after a time tau s1. Tau s1 is the time corresponding to this path length ls1, and tau s2 is the time corresponding to path ls2. And whatever is the field right at the detector, right at the crystal at time t minus tau s2 will become the field at the detector at time t. So the field that we see at the detector, that we have at the detector at time t, is the field, is the sum of the fields, and the first one is the field, signal field at the crystal at time t minus tau s1, and the signal field at the crystal in alternative 2 at time t minus tau s2. So that's why the field at the detector at time t is the sum of the fields at time t minus tau s1 and at time t minus tau s2. So this is also very similar to how we added the field when we did the Michelson interferometer or the one photon interferometer, and the field at the detector was the sum of the fields at two different times in the past. So that's the field operator at the signal, and this field in the alternative 1 and 2 we can expand it like this. This is just a modal expansion, and this works in pretty much the same way as we do in the classical. So this is the time domain representation, and this is the frequency domain representation. The electric field amplitude, here we are replacing this with the annihilation operator. In addition, here we have also added this function fs omega s minus omega s naught. This is the filter function. So typically in experiments one puts a filter. This is the frequency filter, so that one doesn't accept all the frequency but accepts only in the range that is required for that particular experiment. So if it is to represent the experimental situation, then we add a filter function here as well. This CS1 is the attenuation constant and those factors in alternative 1 of the signal field, and ES2 is again the attenuation constant of the signal field phases in alternative 2. And phi S1, phi S2, these are the phases, the extra phases due to reflection, geometric phase and so on in alternative 1 and in alternative 2. So that's the electric field operator, the signal electric field operator, which is the sum of the electric field operators in alternative 1 and alternative 2. Similarly, we can find again the tau S1 and tau S2, these are the time parameter. These are pretty much for these corresponding to these length parameters that we have over here. So we will use time parameters and these length parameters quite interchangeably here, the notation wise, and they are just the time is just length by c, which says c is the speed of light. So just like signal, we can also write the idler field operator, and which will again be the sum of the idler field operator in alternative 1 and in alternative 2. If we expand it, it looks like this. Ci1 and Ci2 are the attenuation factors in alternative 1 and 2 for the idler field, and these are the phases, and Fi, that's the filter function right before the idler detector. So since the detectors are same in the two alternatives, that's why this Fi is same here as it is over here. So that's the these are the field operators. So now once we have the field operators, we have the state. Again, the state is right at the exit phase of the crystal, and we have these operators at the detector in terms of the operators right at the exit phase of the crystal as well. So now we can calculate the coincidence count rate, which is the probability per unit time squared that a photon is detected at the detector ds at time t, and another photon at detector di at time t plus tau. So that's the coincidence count rate, and this we have seen that it is given by this. So that's the coincidence count rate or the probability t and t plus tau, and it is given by the psi, which is the state, and then the signal and the idler electric field operators. This we had discussed earlier as to how this quantity represents the coincidence count rate. Alpha S alpha I, here I am just adding it for the complete picture. These are the quantum efficiency of the two detectors. Okay, so now that we have this, we want to actually evaluate this quantity, and we have all the ingredients here. So for ES, EI, let's just substitute this ES1 plus ES2 and so on. So if we do that, we can represent this as this, where this all these ES and EI, they are represented as the sum of the fields in the two alternatives. So 2 times 2 times 2 times 2, this is a total of 16 terms. But if we do the calculation explicitly, we find that out of those 16 terms, only 4 survive, and those 4 terms are given by this, which are ES1, EI1, EI1, ES1, psi TP1, psi TP1, and then ES2, EI2, EI2, ES2, psi TP2, TP2, and then ES1, EI1, EI2, ES2, psi TP2, psi TP1. This is a cross term, and it's of course it's Hermitian conjugate. So the coincidence probability, or the probability per unit time that one photon is detected at ds at time t and another at detected di time t plus tau, is given by this. We could see that this term RSI11, this is essentially the coincidence count rate if only alternative 1 was there. So if only alternative 1 was there, then that would be the total coincidence count rate. RSI22, that is the coincidence count rate if only alternative 2 was there. But when both the alternatives are there, and both the alternatives can interfere, then we will have these cross terms over here, this and the Hermitian conjugate. So these are the cross terms. So again, we see that the structure of interference here is pretty much the same as we have in the one photon case. In the one photon case also, we have two alternatives, and then the interference, which in that case is in terms of intensity, has 4 terms. Out of the 4 terms, the 2 terms are the intensities coming from alternative 1, alternative 2, and there are 2 cross terms. So similarly over here, now we are not talking about the intensity, we are talking about the coincidence count rate, and then the total coincidence count rate is basically the sum of the coincidences coming from alternative 1 and alternative 2, and then the 2 cross terms. Okay. So now we want to calculate all these quantities. So let's start by just calculating this quantity. Once we have this quantity, then we can see that we can calculate this quantity by just taking the adjoint and changing the index from 2 to 1. Similarly, we can calculate all the other quantities as well. So let's just calculate this quantity first. So this is what we want to calculate. We have all the ingredients again, psi TP2 and EI2, ES2. These are all the terms that we already have. That's a psi TP2, and these are the expressions for ES2 and EI2 and so on. So we can come here. So let's just calculate this. Here we just substitute that the expressions for EI2, that's that, ES2, that's that, and then the state in the second alternative. So that's that. Here we have these are the attenuation constants. Okay, now we can rearrange them a little bit. So here we are just putting all these things together. This omega prime and omega integral, these are corresponding to EI2 and ES2, and we have the two-photon state in terms of the omega p and omega d integrals. So here we are putting all of them together. The C2 we are putting for CS2 times CI2. We are combining these two, and then phi 2 we are putting in place of phi S2, phi I2 plus phi P2. And then we just phi S2, phi I2, and then phi P2 from here. We just collect it, put it together, and since these do not depend on omega P, omega D, they are put outside. That's the pump field amplitude, that's the phase matching function. Here are the filter functions that we have put together, and all these terms we have then put together. These are the two annihilation operators that we have over here in terms of omega prime and omega, and the state, photonic state, is in terms of omega P and omega D. Okay, so now we evaluate the annihilation operator and integrate. Now we see that this AS2, the signal annihilation operator, that is in terms of omega, but the signal state is given in terms of omega P and omega D. So this will act on this term and give us a vacuum state only when omega is equal to omega P by 2 plus omega D. Similarly, this state, this annihilation operator, will act on this state and yield a vacuum state. I mean, this is a one photon state at where one photon is at frequency omega P by 2 minus omega T. So this Eigler annihilation operator will act on this Eigler state and yield a vacuum state only if omega prime is equal to omega P by 2 minus omega D. So the action of this on this and this on that will give us a 2 Dirac delta function, and if we integrate that, we are left with, we'll get rid of the two integrals, and then we are left with just the two integrals, omega P and omega D. These two will actually go away, and we have our vacuum states here after operating these annihilation operators on these states. Okay, so now we will make a series of assumptions. So these are the length parameters that we had defined here. Now for every length parameter we define the corresponding temporal quantity. So for example, tau for L2 we define tau 2 in the same manner as tau P2 plus tau S2 plus tau I2 by 2 and so on. Similarly, for tau L2 prime we define tau 2 prime equal to tau S2 minus tau I2 and so on. Now in order to evaluate this integral, we'll make a few further assumptions. First we'll make the change of variables. So for omega p we are replacing that by omega p prime plus omega naught and omega d by omega d prime plus omega d naught. Here the assumption is that these fields are centered around omega naught as well as omega d naught. We also assume that although the fields are centered at omega naught, but and also the width of the field, that is delta omega p, that is much less than the omega naught, and similarly for this one, the width of the signal Eigler field is much less than the central frequency omega s naught. This is pretty much the same assumption that we did in the case of a quasi monochromatic field that we did in the context of temporal interference. So again, similarly for the Eigler field, we assume that the field, the frequency bandwidth of the field is much smaller than the central frequency of the field. So with these assumptions, then we can write this quantity this as this. So here we are essentially doing the change of variables. So V2 omega p becomes V2 omega p prime plus omega naught, and so on. And since we have assumed that the frequency bandwidths are much smaller than the central frequencies, so we are putting these integrals which are from 0 to infinity to now minus infinity to infinity. So this is just by doing the change of variables. Okay, now we assume that the spectral width of the pump, that is delta omega p. So we have this V2, which is the amplitude of the pump field, and we have this phase matching function. And we have this now these double integral. But now we assume that the width of the pump field is much smaller compared to the phase matching function and the filter function. And we also assume that over the range of omega p or omega p prime, the phase matching function and the filter functions do not change appreciably. So with these assumptions, we can actually separate the two integrals, omega p prime and omega d prime. So omega p prime integral has this, omega the V2, and then the omega d prime integral has the rest of it. Of course, this one does depend on omega p prime, but we assume that the phase matching function and this doesn't change much in this omega p prime range, and that's why we can replace this omega p prime by just its central value. So this central value of omega p prime is omega naught, and then omega naught by 2 is the omega s naught, that is the frequency of the pump. The central frequency of the signal is basically half the central frequency of the pump. So we have these two, we have this one as the two separate integrals. Now let's define two quantities. First is this G2 star t, which is pretty much this one. So this we define as just this quantity with the time argument t. This is a function of t. Similarly, this quantity we define as V2 t, and therefore we can write this one as V2 t plus tau by 2 minus tau by 2, because the definition here is for t, but we have a t plus tau by 2 minus tau 2. So that's the V2 that quantity. Similarly, this definition is for I omega d prime t, and inside we have here t tau plus tau 2 prime, and that's why it's like this. This quantity is this, and now we can go back and calculate this quantity. We already have this, we calculate this in a similar manner, and then this RSI12 can be written like this. So what we have is e to the I minus omega naught delta tau plus omega d naught delta tau prime plus delta phi, and the product of these quantities. Okay, so again this k, we have combined all these different constants and put them all together. Okay, so this RSI 12 t plus tau, that's more like an instantaneous coincidence intensity, that is exactly a t and t plus tau, but in an experiment we cannot make such sharp measurements. So in experiment we always do the averaging. So the averaging over t and then averaging over tau. So in an experimental situation, what we can always measure is this time averaged quantity and time averaged over this t as well as tau. So t time averaging is over this t collect, and tau averaging is over t coincidence. So this is the average quantity we need to now calculate. So for this we do this time averaging now with over t and tau, but let's just realize that this t collect in experiments is typically of the order of a second, that the time over which the temporal the signals are collected is over 1 second, and the frequency bandwidth, the inverse frequency bandwidth of pump lasers, that's of the order of 1 microsecond. And so what we have is this t collect is much larger than 1 over delta omega p. And as a result, this product, this average will then just depend on their difference. So we can write this simply as, this will only depend on the difference of the two arguments. So this is V1 star t times V2, this quantity minus that quantity, which is essentially t plus delta tau, which is delta tau. So that's time averaged over t. This we can just rewrite, this remains here, we multiply numerator and denominator by this quantity, and as we had done before, this stays here, and this quantity we just define as the degree of coherence. So this is time averaged degree of coherence, and it actually depends only on the difference of the two arguments. Similarly, for most down conversion experiment, the T coincidence, the time window over which the coincidences are collected, is of the order of nanosecond, and also the 1 over delta omega, that is of the order of picosecond. This is the time scale over which this is the frequency bandwidth of the down converted photon, that's of the order of picosecond. And so again we have that this time is much larger than this, hence we can do this time averaging over tau, and in this case also this time averaging will only depend on their difference. So this quantity will just be equal to G1 tau and G2 star tau minus delta tau prime, which is the difference of the two arguments. And similarly we can write this quantity in this manner, where gamma delta tau prime, that's the time averaged degree of coherence. So with these two we can now write this time averaged quantity in this manner. This is much more simplified. This V1 square, this is the pump amplitude of the pump in alternative 1, amplitude of the pump in alternative 2. This is the signal idler field amplitude in alternative 1 and 2. This delta tau prime, delta phi, these are all the quantities we had defined in the very first few slides as the important length and time parameters. And then we have these two coherence functions, time average degree of coherence function. One is in terms of delta tau and another one is in terms of delta tau prime. So once we have this RSI 12, we can similarly calculate RSI 21, RSI 11, RSI 22, and then the total coincidence counted we can write like this, where this is R1 plus R2 plus 2 R1 R2 gamma delta tau, gamma prime delta tau prime, and cosine omega naught delta tau, omega d naught delta tau prime plus delta phi. R1 here again we have combined all these quantities together, R2 we have combined all these quantities together. We can also write this in terms of delta L and delta L prime, and then it looks like this. And here we go between the magnitude of the wave vector and the frequency. So we can either use this and this. So we see that this coincidence count rate is written in terms of these length parameters delta L and delta L prime. And although we had 6 different length parameters, LS1, LI1, LP1, LS2, LI2, LP2, what we see that only two length parameters are what's appearing in the final equation. This is pretty much same as what we have in the Michelson or temporal interference, in which only the difference of the time parameters or the distances traveled, delta L or delta tau, is what shows up in the expression for interference intensity. Okay, so what we have obtained here, this is the coincidence count rate in a general two-photon interference experiment. And the general two-photon interference experiment involves 6 different length parameters or time parameters, and we see that we only need to have this delta L and delta L prime, 2 length parameters, and of course this one phase parameter, and we can write it like this. So I will definitely at this point encourage everyone to kind of derive these equations to have a thorough understanding and feel for the math that's involved. Okay, now this is the two-photon interference law applicable for a general two-photon interference. Let's look at some special cases. First we'll look at the degenerate down conversion, in which the omega d naught is 0. That means the central frequency of the signal and central frequency of the idler, they are equal, so the difference is 0. We also assume that the R1 and R2, they are equal. That means the field amplitude coming in the two alternatives are equal. And in that case, we get a slightly simpler expression, that is C equal to 1 plus gamma prime delta L prime gamma delta L cosine k naught delta L plus delta phi. In addition, if the pump and the signal idler field, they have the Gaussian spectra with frequency with delta omega p, delta omega, then we can write this gamma delta L as this Gaussian function, gamma prime delta L prime as this again another Gaussian function, and their widths will then be given by C by delta omega p, and this we can call the signal pump coherence function and the signal idler coherence function. These are the two coherence functions that shows up, and these are their widths. So we find that the condition for two-photon coherence or two-photon interference, and the necessary condition, is that this delta L has to be much smaller than this pump coherence length, and the delta L prime has to be much smaller than the signal idler coherence length. And as long as these two conditions are satisfied, we will have interference, two-photon interference. If any of the two conditions are not satisfied, we will not have two-photon interference. This is same as the interference condition for one-photon interference, where we see that the path length difference has to be larger than the coherence length involved, and as long as that condition is satisfied, we have interference. So similarly in this case, we have two conditions instead of one, and these two conditions are here. The first one is in terms of the coherence length of the pump, and the second one is in terms of the coherence length of the signal idler fields. Okay, now let's look at the two special cases. Case 1 is when delta L prime is equal to 0 and delta phi is also 0. So, in this case the RSI thus takes a even simpler expression, 1 plus gamma delta L plus cosine k naught delta L. So, here we see that as a function of delta L, the coincidence count rate will show interference because this cosine term. But since there is this coherence function as well, as we increase delta L, at delta L equal to 0, this is 1, but as we increase delta L, this will reduce to 0. So, we will have interference, but then that will decay down to 0 within this length LP coherence. So, we see that delta L plays the same role in two photon interference as does the optical path difference in one photon interference. Let us look at another case when delta L is 0 now and delta phi is some fixed quantity. In that case, RSI is C, this one is C1 plus k gamma prime delta L prime, because this quantity is just 1, and since delta L is 0 and this is delta phi is some fixed quantity, then cosine is just a fixed number which is some k. So, in this case what we see here is that if we change delta L prime, we do not see any interference. Rather than we just see the profile of this function gamma prime delta L prime, and if this profile happens to be a Gaussian function, then we will just see a Gaussian profile. So, this has really no one photon analog. Delta L does have one photon analog, but this delta L prime does not have any one photon analog. This is the specific to this two photon interference. Okay, so far this is just we haven't shown an example. In the next lecture I will take one example to actually take one example of particular two photon interference experiment, and so that these things will be much more clearer. But in this lecture I just wanted to do the math in all the details. One more piece that's remaining is that in several two photon interference we also see one photon interference effect. If we just look at one detector, there may be interference effects there. And so here I just wanted to have one quick result. So, and this is and for that I will take one result that we had derived in the first few lectures, and this is the probability of individual event if we know the joint probabilities. So, suppose x and yj are two discrete random variables, and if pxyj is the joint probability, then the individual probability px is just given by this quantity. So, px can be written in terms of the joint probability is px yj. Of course, yj 1 to n, that forms a mutually exclusive set, and so if we know all these probabilities, then we can calculate the individual one. So, the point is, by knowing the joint probabilities, one can calculate the individual probability. Of course, this needs to be a complete set and yj's are mutually exclusive. So, similarly, if we have suppose a photon of the entangled pair is detected at location, the first one, and its entangled partner has the probability of getting detected at n separate locations given by y1 to yn, and of course the y1, these are different locations. So, y1 to yn, this is a set of mutually exclusive random events, and then of course the second one has to go to one of these n, then this will form a mutually exclusive set. And so, in that case, the one photon count rate at Rx at detection position x can be written in terms of these coincidence detection. So, the intensity at Rx can be written as the coincidence of the sum of the coincidences between x and all those yi's. So, we will I mean this is coming straight from the classical probability theory, and that we are using here to express the intensity at individual detectors in terms of the sum of the coincidences. So, we will use this result in our next lecture, but for this lecture we will stop here. Thank you.